So this is the cryptography and network security course. In this course, we are going to learn cryptology that consists of two parts, cryptography and cryptanalysis. Cryptography is the part where we design different types of crypto systems. And cryptanalysis, we try to attack a designed crypto system to understand its limitations. Now the reference books, I will follow mainly, I will follow Starlings and another book, Stenson, and few more books. I will mail you those names of those reference books, as well as the syllabus that I will try to cover. Okay. Now, let us start with an introduction to classical cryptography. So, so what is cryptography? Cryptography is the science or art of secret writing. The fundamental objective of cryptography is to enable two people, Alice and Bob, to communicate over an insecure channel in such a way that an opponent cannot understand what is being said. Consider this communication channel. So Alice and Bob, Alice wants to send X. X is called the plain text to Bob over an insecure channel in such a way that only Bob can learn the message X, nobody else. Oscar should not be able to see the message. So this plain text X, Alice uses an encryption algorithm to encrypt this message X. This encryption algorithm makes use of some key coming from key source. And the decryptor is having the access of the same key. Okay, so the plain text is encrypted using this key, using some encryption algorithm, and Y is produced. This is called ciphertext. Bob, having access to the same key, can decrypt Y and recover the X. And the challenge is to design your encryption and decryption algorithm in such a way that this third-party opponent, this Oscar, should not be able to determine what was the plain text or what was the key. But Bob knows the encryption key and he will be able to decrypt it and get the plain text. So main challenge is to design your encryption and decryption algorithm in such a way that enables us to achieve these goals. And another thing is this key is shared among encryptor and decryptor. Bob and Alice share the same key in this setup. Okay, so how to by some predetermined method they agree on this key. Okay, so how to distribute this key among Alice and Bob so that no one else should be able to know it. That is another issue. It's called key distribution thing. So we will come to that. So encryption, decryption, this is the fundamental algorithm for preserving privacy. Confidentially sending some information so that Oscar should not be able to know. Only intended recipient Bob will be able to know this. Now, so as I said, cryptology is having two parts, cryptography and cryptanalysis. So cryptography is the art of converting information to a form that will be unintelligible to an unintended recipient. This is carried out by cryptographers who design different crypto systems. And another part is cryptanalysis. This is the art of breaking cryptographic systems. This is carried out by cryptanalysts. As I said before, that if you design a crypto system, how good your crypto system is, you have to check that. So that is done by cryptanalysts. So they try to mount attacks. If it prevents those attacks, then it is good, like that. So there are mainly two types of cryptography in use today. symmetric key cryptography or secret key cryptography, where both the encryptor and decryptor uses the same key. This is called symmetric key cryptography. Another is asymmetric key cryptography or public key cryptography, where each user is having a public secret key pair. A pair of keys, one is publicly available, another is kept secret to the user himself or herself. Formally, a crypto system is defined in this way. This is a 5-tuple set of plain text. This is a finite set of possible plain text. C is the finite set of possible cipher text. K is the key space. This is a finite set of possible keys. Epsilon is consisting of encryption algorithms, and this is decryption algorithms. So for any particular key from the key space, there is an encryption rule EK belongs to E, and corresponding matching decryption rule DK belongs to D, where EK is a mapping from plain text space to cipher text space, and DK is a mapping from cipher text space to plain text space. And these two functions are such that decryption of encryption of X will give you back X. Under the same key, using the same key, if you encrypt X and then apply the decryption rule under the same key, you will get back X. For any plain text, X belongs to P. Now, while designing a crypto system, from practical point of view, we need these two things: efficiency and security. So each encryption function EK and decryption function DK should be efficiently computable. Efficient algorithms. Encryption algorithm, decryption algorithm should be efficient. And another one, it should be designed in such a way that an opponent, upon receiving the ciphertext string Y, should not be able to determine the key that was used, or the plain text string X. Okay. So mind that while encrypting, this encryption algorithm, decryption algorithm, these are all published. Plain text is unknown, and the key used to encrypt for encryption, this is unknown. So the process of attempting to compute the key given a string of ciphertext Y, this is essentially cryptanalysis. Okay. So if opponent can determine K, then easily he can decrypt Y, just as Bob would. Bob is having the decryption key. So same way the opponent can get the plain text X from the ciphertext Y if he is able to determine K. So the main objective in designing a crypto system is this: determining K should be as difficult as determining the plain text string X given ciphertext string Y. Okay. So let us discuss few ciphers, classical ciphers. The first one is Caesar cipher. Caesar cipher. So English alphabet is my plain text space. I came, I saw, I conquered. Generally, in English alphabet, plain text are written in lowercase and ciphertext in uppercase. So, encryption rule is each letter here is shifted 3 letters down. I becomes L, C becomes F, like that. A becomes D, like that. And we omit spaces and commas. So, I came, I saw, I conquered. This is encrypted in this way. Ciphertext. So, this is essentially the key. Key is shifting each element, each alphabet character 3 letters down in the alphabet. So, the decryption is very easy. Decryption, given this ciphertext, you have to, each letter has to replaced backward 3 letters. Okay. So this encryption and decryption is done in this way for Caesar cipher. Mathematically, we can think in this way. It's not means this is your correspondence. A corresponds to D. B. So one permutation essentially we are using. This is essentially one permutation of ABC A to Z, where each letter corresponds to 3 letters down for the ciphertext. A is mapped to D, B is mapped to E, 3 letters down, like that. Okay, so using this you take this as exercise. So using scissor cipher, what will be the ciphertext corresponding to this plain text? Meet the Iceman at noon. Very easily you can determine this if you know the size. It is a scissor cipher. So as I said, algorithms, the key we hide. So if you know scissor cipher, then you can obviously know the key is essentially that thing. This correspondence you already know. Okay, so this is essentially not secure. Now shift cipher. In shift cipher, this is essentially one general case. This is the general case of scissor cipher. So we have 26 alphabet letters, and corresponding to that, we can always associate A corresponds to 0, B corresponds to 1, Z corresponds to 25. So over Z26 we operate. So your plain text space, ciphertext space, key space is Z26. Z26 means any integers modulo 26. Any integer you divide by 26, take the remainder. So remainders, the values of the remainders are from 0 to 25. So we are working on Z26. And the key space is Z26. Key is any element from 0 to 25, including 0 and 25. And encryption is simply shifting. As the name says, this shift cipher. Every plain text is also an integer from this. So it is shifted by K. Decryption is shifted down by K. So this is addition, this is subtraction, modulo 20. All operations are done over Z26. Okay? So encryption is this, decryption is this. Very easy. So if you take K to be 3, then it is essentially scissor cipher. So scissor cipher is particular case of shift cipher. So if your plain text is ordinary English text, you can always establish a correspondence between alphabetic characters and the integers from 0 to 25 in this way. A to Z, A corresponds to 0, B corresponds to 1, Z corresponds to 25. So if for the shift cipher, if your K is 11, then plain text, suppose we will meet at midnight. So corresponding to this plain text, you can get this is alphabetic characters. You ignore the commas and spaces, and the corresponding sequence of integers you can get from this table. From your correspondence, whatever correspondence you get, corresponding to that, you can get the sequence of integers corresponding to this plain text. And then your ciphertext, how you produce the ciphertext, you add K with each of these integers and take modulo 26. Okay, so your encryption is X plus K. So individually, each in this sequence, each integer is considered to be one plain text digit. So you add 11 with this, take modulo 26, reduce modulo 26. That means if it is 22 plus 11 is 33, it is more than 26. So you divide it by 26, take the remainder, that is 7. Same way, 4 plus 11, 15, 22 plus 11 again 7, like that. So once you get this one, you can convert it easily to the ciphertext using this association correspondence. So 7 goes to H, 15 goes to P, like that. So this is a ciphertext. Decryption is very easy. Just reverse process from this plain ciphertext. You construct the corresponding sequence of integers, and instead of adding the key with each plain text digit, a ciphertext digit, you subtract 11. Subtract 11 and take modulo 26. So if you take 7 minus 11, that means minus 3. And minus 3 modulo 26 essentially 22. So minus 3 plus 26 you have to take, so 22. Okay. So subtract, and then from this sequence you get the corresponding alphabet. Convert it into the sequence of alphabetic characters. The shift cipher is also not secure. Scissor cipher is not secure. If you know that your cipher text is generated using scissor cipher, as I said, we don't hide the algorithm. Okay, so scissor cipher is not secure, because once you know it is scissor cipher, you know this is essentially shift cipher with k equal to 3. So k key already you know. Shift cipher, how many keys? Possible keys, your key space is size is 26. So there are 26 possible keys. So this is also not secure, because you can try out all the possible 25 keys for exhaustive search. You go for exhaustive search and try which one is giving you a meaningful text. That will be your key. Okay, so this is also not secure. With one example, it is illustrated here. Suppose this is your cipher text. So k equal to 0 means no shifting. So initially this is your string. If you shift by 1, then this is your string. Shift by 2, this is your string. Like that, you keep on shifting until you get a meaningful sentence. Finally, for k equal to 9, I get a stitch in time saves 9. So a meaningful sentence I am getting. So I will conclude my k is k equal to 9. Okay. So once you know your cipher text is generated using shift cipher, you can try out all possible 25 keys in this way, and once you get a meaningful sentence, you can say this is my key. This is not secure, because these are because of the fact that your key space size is small, only 26. So you can go for exhaustive search always. So two exercises are given. It's very trivial exercises. So given this plain text, what will be your cipher text? If you use shift cipher with k equal to 12, straightforward. And if your cipher text is this using k equal to 12, what will be the original plain text? A more general case than the shift cipher is affine cipher. So in shift cipher, we have shifted each plain text digit. In affine cipher, we take linear transformation. We multiply each plain text digit, as well as we also shift. So here, your plain text space, cipher text space, again Z26, but key space is now a pair, AB. A belongs to Z26, B belongs to Z26. So that A is invertible modulo 26. A inverse exists modulo 26. For that, we need this condition. GCD of A26 equal to 1. So encryption rule is affine function. So to encrypt X is your plain text, belongs to Z26, using key K is AB type, belongs to Z26 square. So this is simply AX plus B. Now while decrypting, what you are going to do, so if this is your Y, ciphertext, this is your Y, then from that you have to solve for X. Given Y, you solve for X. So this will be A inverse Y minus B. That's why for decryption we need A inverse. A is the part of the key, component of the key. A inverse we need. And for existence of inverse modulo 26, we need A should be congruent to 26. Okay, so if your ciphertext is Y belongs to Z26, then decryption, this should be decryption of Y. This is mistakenly written. This is Y. So essentially what you have to do, you have to solve x plus b equal to y, this congruence equation modulo 26 for x. Given y, you have to solve for x. Or equivalently, you have to solve ax congruent to y minus b modulo 26. So this should have unique solution for x. Okay. Now y belongs to Z26 means y minus b is also in Z26. So essentially, it is sufficient to study the congruence ax congruent to y modulo 26. Y belongs to Z26. So you know y, you know a, you have to solve this congruence for x modulo 26. So the condition for existence of unique solution for this, if for any modulus m, for this case particularly m is taken to be 26, we have this result. We are going to prove this in time. The congruence x congruent to b modulo m has a unique solution over Zm for every b belongs to Zm if and only if a and m are co-prime. GCD of a m equal to 1. So this condition we are going to need. This is if and only condition. This congruence has a unique solution for x over Zm for every b belongs to Zm, provided a is co-prime to m. So how many such a's are possible? Phi m. Phi m, this is Euler's quotient function, this Euler's phi function. So this is essentially number of integers less than m and co-prime to m. That is number of integers in Zm that are relatively prime to m. So this. So how many a's are there which are co-prime to m? That means GCD of am equal to 1, phi m. So you can see that in this case, the size of the key space is b can be any element from Z26. There is no restriction on b. So b has 26 possibilities. But a, we have a restriction on a. That GCD of A26 equal to 1. So how many such a's are possible? Phi 26. Right? Phi 26. So key space size is phi 26 times 26. So we have this result. Maybe you already know this. For any positive integer, this has unique factorization theorem. From unique factorization theorem, it has unique factorization like this. P1 to the power E1, P2 to the power E2, Pn to the power En. P1, P2, Pn are distinct primes. Ei's are greater than 0, and they are less than I is less than I is 1 less or equal to I less or equal to N. Then phi m is given by m times product 1 minus 1 by pi. We are going to prove these things before introducing asymmetric key cryptography, public key cryptography. Before that, we are going to discuss these proofs. Okay? So this is the formula for Euler's torsion function, and you can find this provided you explicitly know the prime factorization of m. To calculate this, you need to know these PIs. What are the prime factors of m? So, for example, m equal to 26 in this cipher, shift cipher. This is not shift cipher. This is affine cipher. Okay, so m equal to 26. So phi m is phi 26. That is phi 13 into 2. So if you use this formula, this is 26. 1 minus 1 by 13. 1 minus half. 12. So how many integers are there? That means a's are there which are co-prime to m? 12. And you can write this a's explicitly which are co-prime to 12. Co-prime to 26. Okay. So you can see encryption algorithm is this affine function. B having possibilities 26, A is having possibilities 12. So key space size is 12 into 26, 312 possible keys. This is also too small to be secured. Key space size is 312. So you can go for brute force search to find the key. Exhaustive search, you can go for exhaustive search. So if you define your affine cipher over Zm instead of m equal to 26, other m, general m, then it is m into phi m. So if your alphabet, underlying alphabet is having 60 characters, alphabetic characters, phi 60 is essentially 60 prime factorization is 3 into 2 square into 5. So you can apply this the above formula. I 60 is 16. So in that case, key space size is 960. Okay. Now this is one illustration, an illustration with an example of affine cipher. Suppose your key is 73. 7 is co-prime to 26. So this is a valid key. 7, 3 both are less than 26. Okay. Now 7 is co-prime to 26 and 7 inverse modulo 26 exists. And now you are going to need this because encryption algorithm is simply ax plus b, 7x plus 3 for any x belongs to Z26. Decryption needs 7 inverse. This key is essentially 7 inverse you are going to need. Now you have to have a way to calculate 7 inverse modulo 26. Now since your modulus is 26 very small, you can go for exhaustive search. 7 inverse into some element from Z26, when you multiply, it should give you 1. Okay, so you can try out all the values in Z26, that means 0, 1, 2 up to 25 and check which gives you, which when multiplied by 7 gives you 1. So 7 into 0, no, 7 into 1, no, 7 into 2, means every time you have to multiply and take modulo 26. You have to, if it is more than the multiplication, after multiplying you get a number more than 26, then you have to divide it, take the remainder, mod operation. Okay? So you can check the 15 is the number, 15 into 7 modulo 26 is giving you 1. So 7 inverse is 15. For this example, I need 7 inverse modulo 26, but in some other problems we will see it might be very large. So it is instead of 226, it may be 269 suppose, or 269 or 261 suppose, or maybe instead of 3 digit, it may be 10 digit. So how to find the inverse modulo the very big number? There is an algorithm known as extended Euclidean algorithm that can be used to find the modular inverse. So those things we are going to discuss in this course. Okay, so encryption of x is simply 7x plus 3. Decryption of y is 7 inverse y minus 3. So 7 inverse is essentially 15. So 15y minus 15 into 3, if you multiply and take modulo 26, it is 90. And you can check that encryption of x, if you apply on this, the decryption, you will get back x over Z26. All operations are over Z26. Okay? Modulo Z20, modulo 26. Now suppose your plain text is HOT. So we have this correspondence of alphabetic characters with the integers in Z26. So A corresponds to 0, B corresponds to 1, C corresponds to 2. This we already have. So corresponding to HOT, this is your sequence. Now to encrypt each plain text digit, you encrypt separately. This one you separately encrypt, apply the affine cipher. 14 apply the on 14 apply the affine cipher. So on 7, if you apply the affine cipher, your key is 7. Your key is 7 3, and encryption is 7x plus 3. So x is 7. So 7x plus 3, 14 into 7 plus 3, 19 into 7 plus 3. So you calculate this, take modulo, first one giving you 0, second one 23, third one 6. So this is your encrypted cipher text. And corresponding letter, the corresponding sequence of alphabetic characters from this table, you can get this A, X. Okay, so from this ciphertext you can easily get the plain text if you know the key. Your AV key is so for decryption you have to apply 15y minus 9. So if you receive your ciphertext this, you can get this sequence of integers. So each integer is your y. So you have to apply this rule, 15y minus 9. So for corresponding to A, you get 15y means this 0, 15y minus 19 modulo 26. This is this corresponds to H. X is 15 into 23 minus 19. Okay, so you can simplify, calculate this, and this G corresponds to 6, and this G is 15 into G corresponds to 15 into 6. 15 into 6 minus 19 gives you 19. That corresponds to T. So you can check this, that if you are given the ciphertext, you know the key, you can easily invert it and get your required intended plain text. So here, as I said, that exhaustive search, this is not secure, because exhaustive search, if you go for exhaustive search by trying out all the possible 312 keys, you can always get a key. Okay, so because your key space size is small, only 312, it is not secure. You can go for brute force search, exhaustive search. The next generalization is substitution cipher. A substitution cipher, so P and C, the set of 26 letters English alphabet. P is A to Z and C is bold letter, uppercase letter we are writing A to Z. And here the key is the set of all permutations of 26 alphabetic characters. Okay, so key is one permutation. How many permutations are possible? 26 factorial. So now key space size is made very huge. Key space size is 26 factorial. And one of these permutations is your key. So you take one permutation phi belongs to, this should be K, okay? Phi belongs to K. Phi is key. Phi belongs to K. So encryption of each plain text symbol, each plain text symbol, simply you just give the permutation phi x. And decryption is simply phi inverse x. If you know phi, you can easily calculate the phi inverse. For example, let us take this permutation. So A to Z, A is permuted to X, B is N, C is Y, like that. One permutation I have taken. Okay, so it means E of phi A equal to X, E of phi B equal to N, like that. Okay, so this is one permutation. And decryption is uses the inverse permutation. So phi inverse is given by simply this is ABC. Now from the second row of this, you can see A is this, what is A? A is mapping to D. So A is mapping to D. B is mapping to L. B is mapping to L, like this. So if you fix your phi, you can always know phi inverse. Very easily you can get it. Now how to encrypt? So you do it by yourself. Suppose you are given the ciphertext this. What will be your plain text? This is your key. This phi is your key. So phi is your key. That means phi inverse. You have to apply phi inverse while decrypting this. And you check. This essentially gives you this string. This ciphertext can be decrypted. This line. You check that thing. Now some points to note here, that whatever ciphers we have discussed so far, all are monoalphabetic cipher. What we mean by monoalphabetic cipher? Each alphabetic character is mapped to a unique alphabetic character. Here I have taken a permutation. A to Z, one permutation, the second row corresponds to one permutation of that. A is going to X. A is going to only X, not any other element. B is going to N. C is going to Y. So always, it always goes to the same alphabetic character. So each alphabetic character is mapped to a unique alphabetic character. This is monoalphabetic cipher. So far, all the ciphers, all the ciphers we have discussed so far, all are monoalphabetic cipher. Okay. So in this substitution cipher, we use arbitrary monoalphabetic substitution in the substitution cipher. So there are total 26 factorial possible permutations. This is very large number, 2 to the power 88. So if you go for exhaustive search to find the key, which is one particular permutation from this set, from this collection of 26 factorial permutations, it is very difficult. It will take very long to find the key. So exhaustive search or brute force attack is infeasible in this case. However, we will see later that the substitution cipher is not secure. It is actually insecure against frequency analysis. So I will discuss what we mean by frequency analysis in the next class. Okay? So some points to note here. Shift cipher is a special case of substitution cipher. And in shift cipher, we are shifting each plaintext digit by k. K is an element chosen from 0 to 25. So there are 26. So out of these 26 possible permutations used in substitution cipher, we choose only 26 keys, 26 particular permutations. Okay, so shift cipher is a special case of substitution ciphers which include only 26 of these factorial 26 many possible permutations of 26 elements. Affine cipher. Here, affine cipher is also, this is also a special case of substitution cipher, which include only 526 into 26 many. So this is our affine cipher is tuple AB such that A is co-prime to 26. So total possible cases, total possible values of the key are 526 into 26. So there are 312 possible pairs AB. So that A is co-prime to 26. So this many permutations actually are picked for affine cipher out of 26 possible permutations of 26 elements. This is particular case of substitution cipher. Now, as I said, all these ciphers are monoalphabetic, and monoalphabetic ciphers is having all the monoalphabetic ciphers is having this problem. It's called frequency analysis. Frequency analysis. If your plain text is English alphabet, then we can mount frequency analysis. We will discuss this later. So to resist this, polyalphabetic cipher is proposed. So it uses different monoalphabetic substitutions while moving through the plain text. So in the plain text, different suppose A is appearing in different places. Now, when you encrypt it, A is not always mapped to the same alphabetic character. A may be going to V, another A in that plain text may be going to H, like that. So this it uses different monoalphabetic substitutions while moving through the plain text. So one example is the Virginia cipher. This is a polyalphabetic cipher. We will discuss Hill cipher also. That is also polyalphabetic cipher. Let us now discuss Virginia cipher. The Virginia cipher. So suppose M is a fixed positive integer. Your plain text, cipher text, space, plain text space, cipher text space, key space, all are M tuples. So here what we do, if you have a string of, means your plain text essentially is divided into blocks of size M. Key is also M length key. m length string over Z26, and encryption just x1, x2, xm, each digit is shifted k1 times the first one, k2 times the second one, km times the mth digit, like that. And decryption is simply the reverse, y1 minus k1, y2 minus k2, ym minus km. All operations are performed over Z26. It is like your key is a key stream of length m, and each block of size m in the plain text is just added with this key stream in that order. Ciphertext is produced. While decrypting, you use the same key stream, and instead of adding, you just subtract. Take the modulo 26, all operations over Z26. Now here you can see that your key space size, this is the set of all possible m tuples over Z26. How many such possible m tuples are there? 26 to the power m. 26 to the power m. K1, 26 possibilities, K2, 26 possibilities, Kn, 26 possibilities. So key space size is 26 to the power m. This is exhaustive search. If you go for exhaustive search, it requires long time. For example, if you take m equal to 5, key space size is like this, greater than 1.1 times 10 to the power 7. So exhaustive search by hand is impractical, but you can go for computer programming. It is not infeasible for going for exhaustive search if you use computer programming. Anyway, okay. So to make exhaustive search impractical even for computer, you need to make your block size very large. Okay. So suppose m equal to 5 and keyword is a 5 length string. Okay, and here is, we have the correspondence between the English alphabet characters and Z26 elements in this way. A corresponds to 0, B corresponds to 1, Z corresponds to 25. Keyword suppose money. This should be m length vector. Plain text is m length string. Key is m length string. Ciphertext is also m length string. So if keyword is money, corresponding sequence of integers corresponding to this money is this. M is 12, O is 14, like that you can write it. Now suppose your plain text is Viva la France. Viva la France. Your plain text is Viva la France. So you ignoring the commas and spaces, you divide the whole plain text into strings of length 5, blocks of length 5. So and below it you write money, money, okay, like that. So and then I add modulo 26. So what we are going to do, plain text corresponding to this alphabets, string of alphabets, we get this sequence using this table. Okay? And keyword is money, so I will write below this money, 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 and 5 blocks of size 5, and add modulo 26. So it is, if you add, is 33 more than 26, you divide 33 by 26, 7. Okay? So similarly, so you get your ciphertext to be this one. Now you can check that this V, there are several V's, one V here, one V here. This V is substituted by H. This V is not substituted as H, it is substituted as I. Here there is one A, there is another A. This A is substituted as M, and this A is substituted by another alphabetic character E. So this illustrates that this is essentially a polyalphabetic cipher. So decryption process simply same. Your ciphertext corresponding sequence you write, and keyword also below that you write the keyword, and instead of adding you just subtract and take modulo 26. Whatever sequence you get, you convert it into the characters using this table. Okay. Instead of adding, you have to subtract modulo 26. Now, here are some points to note. In Virginia cipher, having keyword length m, if your keyword is having m distinct, means all the alphabets appearing in the keyword is distinct, an alphabetic character can be mapped to one of m possible alphabetic characters. Okay, assuming that the keyword contains m distinct characters. Virginia cipher is polyalphabetic, as we have illustrated by one example. Cryptanalysis is more difficult for polyalphabetic ciphers than the monoalphabetic ciphers. Seal cipher is another polyalphabetic cipher. We are going to discuss it next.